So in this video, I want to go back to a limit that we played with in section 1.3. We used Mathematica to study this limit, and it looked like this limit was equal to 1. That's what our numerical evidence strongly suggested, and so it turns out that it is 1. This is just a fact. I'll call it a theorem. But I wanted to show you how you can do a cute little proof by picture to see why the limit is 1. That's one of the joys of doing math, is you get to often understand why. We can't do that for everything in this particular course. You need a truly proof-based course to get to always see why. But this is one thing that we can see, so I wanted to do it with you. So this is a picture of the unit circle. So unit circle has radius 1. Let's squeeze in a little radius. This is 1. This is 1, right? Radius 1. Okay, I'm going to erase those now. But that's key, that you recognize this length is length 1. And so what I did was I went up some angle theta here. I'm assuming that my theta is less than or equal to pi halves, bigger than 0, less than pi halves. And so I went at the intersection point and I dropped a vertical straight down. I can do that. And then I also intersected from this intersection point here down to the x-axis on the circle, and then of course we can shoot this line all the way out, and we can shoot straight up like this, a tangent to the circle line, and we get a picture that looks like what I've got. So I'm interested in 3 different pieces with you. I'm interested in this this triangle right here. Hopefully you can see that one. And I'm interested in this angle right here. Hopefully you can see that one. And I'm also interested in this larger triangle right here. Hopefully you can see that one as well. And so that's the plan. And I want to simply together compute the area of these 3 pieces. So we have this triangle, we have the pi wedge, I'm going to think about it, and then we have the big triangle. And I want to compute their areas, and I claim that it's easy to see from the picture that this area is smaller than this area, which is smaller than this area. So hopefully that's clear to you. Let's slide these over so we have a little more space to work, and let's begin. So for the first area, you know that the area of this triangle, is 1/2 times the length of the base times the height. So 1/2 base times height. And it all comes down to, what is this height? Well, think about it with me. I know that, let's see, opposite of this angle, opposite over hypotenuse is sine. So I know that sine theta is h over 1. So that tells me, which is just h. So that tells me that h is actually equal to sine theta. And now I can write down the area. So the area of the little triangle that we're dealing with is 1/2. The base we know is length 1 because we're working on the unit circle. 1/2 times the base times the height. The height is sine. So I just get sine theta over 2. That wasn't so bad, was it? We got the area of that one. Okay, area of the pi wedge. Well, anytime you want the area of a sector when you're working in radians, you know that the area is 1/2 r squared theta. What's my radius? My radius is 1, so this is just going to be 1/2 times 1 squared times theta. So this is exactly theta over 2. Now, I just happen to know that formula. If you don't know that, why don't you pause the video and go quickly Google the area of a sector, and you can see the formula and catch up on that. Either way, we're good to go. So now I'm looking at this big triangle. I know that the base here is 1, so we can put a 1 there. And I also know, well, that's about it. So let's see what we can write down. So I want to figure out what this side is. So think with me. Let's call this side, I don't know, we'll call it L. And I know that the tangent of theta is equal to opposite over adjacent. So tangent of theta is L over 1. So the point is, this L is tangent of theta. This L right here, this length of this side, is exactly tangent of theta. I'm actually going to erase that and just write down tangent of theta. That's the length of this side. And so the point is, the area of the big triangle is 1/2 base times height. Base is 1, height is tangent, so I get tangent theta over 2. So I've got my 3 areas computed, and I can see that the following relationship holds. I can see that the first area of the non-right triangle, sine theta over 2, that's clearly less than or equal than the area of the sector, which was theta over 2, and that's clearly less than or equal to the area of the big triangle, which was tangent theta over 2. Let's go ahead and clear the 2. We don't really need that 2 there, so now we can say, all right, sine theta is less than or equal to theta, which is less than or equal to tangent of theta. And now I'm going to do something a little bit crazy. So I'm interested in sine theta over theta, and I don't see that here. So I could divide everything by theta if I wanted to, and that would give me my sine theta over theta. But it turns out I'd be stuck with a tangent theta over theta, which is even worse. So I'm going to divide everything by sine theta. So when I divide everything by sine theta, I get, well, 1 is less than or equal to theta over sine theta is less than or equal to, think with me, tangent. Let's do this to the side. Tangent is sine theta over cosine theta. We're dividing by sine theta, so we get 1 over cosine theta, correct? And by the way, sine theta, when theta, our angle theta, is between 0 and pi halves, you know that sine theta is positive, so you're safe dividing. It doesn't change the inequalities. And now I'm going to take the reciprocal of each of these. I can flip these, and when I do, I change the inequality. And so the point is I can conclude that 1 is greater than or equal to sine theta over theta, which is greater than or equal to cosine theta. And now let's just make the observation that the limit as theta goes, I do need to say 0 from the right of cosine theta. Well, this is just 1. Cosine of 0 is 1. And so, look, this is going to 1, and this is 1. And so the squeeze theorem, I'm done, tells me that the squeeze theorem tells me that the limit, technically for now, as theta goes to 0 only from the right, of sine theta over theta is in fact 1, but it turns out we can actually use the fact that sine theta over theta is even. And so that means that the limit as theta goes to 0 from the left of sine theta over theta is going to be exactly the same as the limit as theta goes to 0 from the right of sine theta over theta. And both of these are just 1. And so finally we can conclude the thing that we set out to show, which is the limit as theta goes to 0 of sine theta over theta is 1. And so I'm going to write that down, again down here. Limit as theta goes to 0, sine theta over theta, this is 1. And I'm going to box it, and I want you to make sure that you know that limit. It's very, very important.